Hello, everyone. So today we're going to continue our conversation talking about chemical kinetics by focusing a little bit more on reaction orders. So last time we were able to help distinguish one of the ways in which you can confirm the reaction order of a complex system. However, today we want to focus a little bit more on what this means in terms of kinetic behavior. So let's go ahead and focus in on three of the most common kinetic forms: zeroth order, first order, and second order. So the simplest form of a reaction is a zeroth order system. So this is going to be a system at which the rate is determined by a constant value and the concentration of the reactant to the zeroth power, which means that any concentration to the zeroth power is just one. In other words, the rate is constant. And this actually is very cool because if we're looking at the consumption of a species, this means that the concentration of A, which in this case again is a reactant, is going to decrease at a steady rate. And again, so as long as you know the rate constant and the time that's elapsed, you can figure out how much of your reactant has been consumed. However, we often like integrating these forms so we can determine the change in the concentration of our reactant. So if we go ahead and integrate the form, what we have is going to be just simply delta A, which we're going to represent as A minus initial concentration of A. And all of this is going to, again, be equal to negative of the rate constant, because, again, we are consuming the system because we're looking at the reactant, times the time that's elapsed, which we're going to quickly rearrange into a linear form by moving our initial concentration over to the right-hand side. And as you may notice, one of the reasons why we like this equational form is it makes a linear fit. So if you can plot the concentration of a species versus time, this means that we're a zeroth order reaction. And I know zeroth order feels like a little bit of a gimme, but in truth, zeroth order reactions tend to happen quite frequently. So a good way to think about a zeroth order reaction is if we have a species that is essentially just in so much excess that it won't be a crucial part of the reaction, because it will never be limiting. So one way to think, one classic example of this is in cases where adding a little extra catalyst won't end up changing the concentration. Other common examples are if I have a multi-step reaction and it turns out that species A isn't involved in one of the rate controlling steps. It's important at some later point in time. So at this point, it's just the consumption of A is going to be entirely dictated by other factors. So one of the important things to be thinking about when we're talking about this case is oftentimes we're not true zeroth order in A, we're often pseudo zeroth order, where essentially other controlling factors have just limited so that in this case of reactions and circumstances, A doesn't play a role with the mechanism. And this is one of the reasons why it's important to be able to identify a zero order reaction. However, one of the other good ways to try and treat a reaction system is to determine its half-life. So this would be essentially how much time is going to elapse till I've consumed half of my initial starting material. And when we treat this for a zeroth order reaction, the idea is fairly straightforward. I'm going to plug in a value for A of A naught halves. So essentially my ending result is going to be half of what I started with. And then you can go ahead and solve this equation. And what you're going to find is that the half-life is dependent on the concentration of A at the beginning and the rate that I have. And again, this should make sense if I have a faster reaction or an increased rate. I'm going to see faster consumption, so it's going to take less and less time to consume half of my material. Similarly, if I have more starting material, since consumption is at a faster rate, it's going to take me longer and longer to get to that point. So while we often think about half-lives as being concentration independent, that is not the case for a zero order reaction. And that's important to essentially acknowledge. However, that does bring us to our next reaction order, which is the first order reaction. So these are very common reactions. And this is essentially any sort of reaction where I'm dependent on just the concentration of my reactant. So in this case, I may have reactant A reacting with something else. So this may be a first order reaction, or it may be a first order in one reactant and a first order in another reactant. But regardless, if I have a simple dependence upon the concentration of my reactant, such as things like nuclear isotopes, we can express this as the rate of consumption of A being dictated by the rate constant and the concentration of A. And again, this will give us the consumption of A with respect to time. And we can go ahead and imagine this sort of behavior because what you'll notice here is that the consumption, the rate of reaction is going to vary with concentration. So it's going to be very fast here at the beginning. And then as we get further and further out, the rate of reaction slows down. And so that does make the analysis of these systems a little bit trickier. However, one of the ways we can analyze these systems is like before by integrating our rate law. However, to do that, we're first going to want to move all of our time dependencies to one side and all of our concentration dependencies to the other. And when dealing with the concentration of A, well, that does give us a classic form. Who doesn't love the derivative of A over A? Because that's just going to be the natural log, while the time dependence is just going to be negative KR of T. So this is actually a quite nice and pretty integrated rate form. However, as before, we like to try and present this in a linear form. So we do this by essentially subtracting, by adding the natural log of A naught to both sides, eliminating it from this side and moving it over to the right-hand side. So this gives us a way to determine our rate constant and often initial concentration of our system simply by plotting the natural log of the concentration of the system versus time. So this is a classic mechanism where you will go ahead and try and monitor how the concentration of some reactant decreases over time, often with something like a UV vis spec if we're dealing with a colored reactant species. And when you do this, if you get a straight line by plotting the natural log of A versus time, you should end up being able this should help confirm the presence of a first order reaction. And as a nice benefit, you get your rate of reaction as your slope and your initial concentration as your intercept. So this can be a very useful way of determining these two parameters for a system. However, as before, we're often interested in the half-life of said system, which again can be obtained simply by inputting the half of the initial concentration as your current A. And when you solve for this, what you'll find is that the half-life is going to be given by the natural log of 2, essentially from these natural log terms, over the rate constant. And this actually yields a very pretty feature of first order reactions, namely that they are concentration independent. Because what ends up happening is that while the rate itself speeds up, the rate constant essentially staying the same helps kind of correct for this feature. And so it's always going to take the same amount of time for the concentration to half, no matter where you started. Now, if you think about it, that means at the beginning, when you start with a lot more concentration, you have a fast reaction. But as you go further and further on, your initial concentration decreases. It still takes you the same amount of time to get halfway there. And at the end, what you end up with is a bit of Zeno's paradox, where it will take you infinitely long to get to a concentration of 0. So this is something to kind of keep in mind when dealing with first order reactions. And one of the reasons why so many radioactive isotopes tend to linger in the environment, because they tend to follow these first order reaction behaviors. However, not to be ignored is the classic second order reactions. So you can think of many dimerization reactions as following second order reactions, where it takes 2 of my reactant molecules to combine to drive a reaction forward. So again, by definition, a dimer requires two reactant molecules to form your end product. So not too surprisingly, most of these follow second order reaction behaviors. And again, we can treat this with the same analysis of watching how the concentration of A decreases with respect to time. And we are also going to want to integrate this form, which means we want to move all of our time dependence to the left-hand side and all of our concentration dependence to the right-hand side. And while these aren't quite as familiar as the integral forms of the last two, they are still should be quite familiar, as our concentration dependences will end up yielding the difference of the inverse concentration. So 1 over our final concentration minus 1 over our initial concentration. And all of this is going to be equal to Kr of T. If you're wondering where that negative sign came from or went to from the Kr, it essentially disappeared to cancel out the negative sign that comes from the integration of an inverse form. So this ends up giving us a nice integrated form. And one of the biggest things I want to kind of point out graphically is that qualitatively this does look similar to a first order reaction, but qualitatively the biggest difference is you tend to see a much harsher drop off at the beginning portion because of this squared dependence, and a much slower drop off at the end because, again, with a low concentration, we emphasize this slower drop at low concentrations. So again, second order concentrations tend to be very fast at high concentrations and very slow at low concentrations. However, in order to try and analyze this behavior, we often will again try to linearize our equation. And we can do this by simply moving our initial concentration over to the right-hand side. And it turns out that you can derive second order behavior by trying to form a linear plot of 1 over concentration versus time, and you should essentially see a linear decrease. And when doing this, it's also very beneficial because, again, you're able to pop out as your slope, your rate constant. And again, you can also obtain your initial concentration from your intercept. And finally, we also want to try and determine the half-life of one of these systems, which can be obtained by simply, again, putting in A naught over 2 over here, which would be 2 over A naught, because who doesn't love inverses? And then solving for the system gets us a half-life that exhibits a time dependence of 1 over the rate constant times the concentration. So again, like zeroth order reactions, the half-life of a second order system is going to show a time dependence, or is going to show a concentration dependence. Because again, as I pointed out, we tend to get very fast reactions and short half-lives at high concentrations, and very long half-lives as I go further and further out and have very low concentrations. So again, this is an important thing to keep in mind when you're dealing with a second order system. You can also apply very similar behaviors to determine an integrated rate form for third, fourth, fifth, or even sixth order reactions, as they all tend to follow this same trend, where the only major difference is you're going to just change the exponent, which will give this a slightly different integrated form, but follow most of the same general rules. However, it turns out that, as we've talked about before, most reactions aren't always dependent upon the concentration of a single species. So one of the big questions we should ask is, what does a reaction order look like if it's respect to multiple species? So again, we aren't really going to see this if I have a zeroth or first order, because they can only have one concentration present. However, if I get to second order concentration or second order reactions, they can have a rate dependence on 2 different concentrations. So let's go ahead and look at this elementary system. A plus B goes to products. This is a very common sort of reaction scheme. So if we analyze this system, what we should do is we should be able to see the change in the concentration of A with respect to time as decreasing according to the rate constant and the concentrations of A and B. This is straight from the definition of a system with first order A, first order B. But what is this going to kind of look like in terms of the rate? Well, here's where we run into some slight issues, is trying to figure out how to define the system. So what I can say is that, well, the change in A for this system, since again, we have a reaction coefficients of 1, well, 1 A is going to change as the extent of reaction, which here I'm going to represent as X. For every 1 mole of reaction, I'm going to consume 1 mole of A. So I can go ahead and treat my change in concentration of A with respect to time as the change of X with respect to time. And where this comes in really useful is it gives me a way of describing how describing the concentration of A and B at respect to any point in time, because the concentration of A will simply be the initial concentration minus the extent, and the same thing for B. So then I'm going to use my same trick. I'm going to move my time dependence over to the right-hand side. It's going to go hang out with the rate constant. And then I'm going to have a little bit of fun and move everybody else to the left-hand side. And when we do this, well, then we have to figure out how to try and solve the integral. So I won't spend too much time on the actual integral. Have fun with some with some chain rules. But when you apply the chain rule, what you end up with is you have a set of coefficients with respect to the initial concentrations of B and A that pop out front. And then inside you have terms that have the natural log dependence of A naught over A naught minus X, and the same thing with B, where it's again going to depend on one way to view it, the initial concentration of A and the final concentration of A, initial concentration of B and final concentration of B. But again, all put in terms of the extent of reaction. So because of that, I can go ahead and collapse my extent of reaction back down. I don't need it to help solve the integral anymore. So what I can do is, along with collapsing down my current concentrations of A and B, I can go ahead and move my difference of concentrations of my initial concentrations over to the right-hand side as a prefactor. And then I can go ahead and simplify this left-hand side a little bit more by using our favorite friend, log laws, where I can go ahead and give this system, treat this system as the natural log of the ratio of the concentration of B over its initial state, because again, with a negative sign, I can go ahead and inverse the direction. And I'm also going to, for consistency's sake, also inverse the concentration of A, which means it goes on the denominator. So again, the ratio of B to initial concentration and the ratio of A to its initial concentration, all equal to the difference of my two initial concentrations times the rate constant times temperature. And again, it is worth noting, you could go ahead and inverse the system. You switch the order of A and B, and then you'll switch the order of the addition. Of the subtraction, this will essentially keep any signs consistent. However, you may notice that this is not quite as simple as our second order reaction integrated rate form, or even our first or 0th order reaction mechanisms. However, this is how you need to treat a system where the concentrations of A and B are fairly similar. So this is something you should be keeping in mind when you're dealing with mixed order reactions. So when we have both A and B at near identical concentrations. However, we can simplify this system if I assume that I had a much larger initial concentration of B than A. So the first thing that you may notice is that this difference over here is simply going to disappear, and it's just going to become the initial concentration of B. We're also going to do a couple other rearrangements, mostly splitting up this big natural log term. So I'm going to pull out the natural log of A as negative natural log of A and leave behind the natural log of B over here on the right-hand side. I'm also going to remove the natural log of A naught over B naught. So essentially adding that to eliminate it from my natural log expression. And so it can hang out over here on the right-hand side as my set of initial conditions. Because again, this mimics what we did in many of our other integrated rate laws, where we try and keep all of our initial concentrations hanging out over here. So when we do this, we can also simplify the system a little bit more. I'm going to also move this natural log of B over to the other side and integrate it into this natural log term as well. And then all I leave behind is negative natural log of A equals this term with respect to time and this nice fun ratio of concentrations, of initial concentrations in B. But here we can make another fun assumption. Because the initial concentration of B is so much greater than the initial concentration of A, it really won't change with time, which means that B is pretty much the same as B naught. So it's going to go ahead and disappear from here. So when I do this, what I'm going to end up leaving behind, and I do apologize, this should have been a negative here. What I'm going to end up leaving behind is natural log of A equals the concentration, the negative concentration of B naught KRT plus ln of A. Hopefully this looks familiar because what we did is we just regenerated first order kinetics. So this helps show how pseudo first order kinetics works. It is actually possible to turn your rate constant from a pseudo first order plot to the overall rate constant as long as you know your initial concentration of B. Because again, as we said before, the effective rate constant is equal to the real rate constant times the concentration of B, which shouldn't be changing. So this is one way to try and be able to back out the behavior of a mixed order system. So again, this helps walk you through a nice, simple second order system, first order in A, first order in B. However, occasionally you might have to embrace systems where A and B may be much higher than first order, and watch out, C might get involved too. However, next time we're going to take a step back and acknowledge the fact that some systems don't universally proceed in one direction. There may be equilibrium. Until then, take care.